Good afternoon, everybody, and good morning in the US. My name is Charlie Nicklin. I'm the Chief Exec of IAgrE, and I'd like to thank you all for joining our August presentation. For today's lecture, I'd like to welcome IAgrE member Paul Mwaze from the University of Illinois in the US, who's got up nice and early to talk to us today. Paul is an agricultural economist and project manager of Scapes, which is based at the Institute of Sustainability, Energy and Environment at the university. Paul will discuss the economics of using land for both food and energy production, which is part of a US Department for Agriculture funded project to improve scientific knowledge in this area. As usual, our lectures, everybody will be muted, and if you'd like to ask questions, please pop them in the chat at the bottom of the screen, and then at the end of the presentation, we'll unmute you so you can ask in person. Okay, I'll now hand over to Paul.
Thank you so much for the kind introduction and for the invite to be on the call today. I'm pleased that you made time to come and listen to me and some of the work we're doing in this project, combining solar energy with crops. So let me try and share my slides. So I'm part of a big team here. The project is called Scapes, as mentioned in the introduction. And we are looking at sustainable ways of co-locating agricultural production and solar energy systems. We're funded by USDA. We are collaborating with 3 or 4 other major universities. We are the lead university at Illinois. We're working with Arizona, and we are also collaborating with Colorado State University. At the same time, we're working with the National Renewable Energy Laboratory in Colorado. And the idea is increasingly, there's a lot of interest in deploying solar technology on ag land. A lot of solar developers are coming to the Midwest to look for land to install solar energy. And so we're looking at optimizing the co-location. We see this as an opportunity for rural farmers rather than a threat. And so we have a team that is looking at the engineering aspects and focus on the economics. And we have people looking at the crop science, and we have social science research going on as well. The idea is to look at what makes sense and for which region. So there's a lot of studies on agrivoltaics globally. If you look in Australia, if you look in Germany, there's a lot of studies that have been done. Most of those studies are based on they're really small case studies, 3 hectares and 5 hectares. And the issue is scaling it across a larger region. So what this project is trying to achieve is to develop, look for the conditions under which agrivoltaics is most profitable for a given region. That's why we have 3 regions in this study: Colorado for the grassland area, Arizona, which is a dry land area, and here in the Midwest region of Illinois. And so today I'll be speaking a lot about the economics, but I am a member of IAgrE and I keep my membership. These days, though, my bread and butter is economics. I do mostly cost-benefit analysis, looking at costs and benefits of environmental and agricultural projects. So I'm going to speak more generally. I won't be able to go into all the details of the calculations we're doing because a lot of this work is still in progress, but I'll try and share as much as I can. I think I've already, that slide is basically really a summary of what I've just said. That picture is really cool. That is one of our project sites in Champaign County here in Illinois. So this is Solar Farm 2.0, and we got permission a few months ago, actually plant crops in between rows of solar panels. And so as you can see, I'm not sure you can see that, but that's sorghum. That's short sorghum that is now actually doing really well. There's been some rain, and so sorghum is growing in between the panels. This has not happened before. And so the idea here is if we maintain electrical output from the solar panels, plus any crop yield that is going to be achieved in between the panels, in theory, that should represent an improvement in income if we hold the electrical production output from the solar arrays. And so we're trying to, this is sort of like a proof of concept. We're trying to show that this can be done. And so this is one of the project sites that is now beginning to show some of the crops that can be planted in between panels. We also have soybeans in other rows between panels. So I'll keep going. And so the question is, what's the motivation for this research? Why we got funded to do this? Why is there a lot of interest in agrivoltaics? Agrivoltaics is considered very promising, is gaining traction globally. I looked at the headlines in the UK. There's a lot of nice headlines. There's a lot of interest in doing agrivoltaics because it provides options to reduce land use competition between solar and agriculture. It allows continued use of the land for farming, even when solar panels are installed, and potentially increases crop yield under extreme heat conditions. So some crops get protected from extreme heat, preserving soil moisture. Obviously, you're using the land for two activities, both electricity production and crop. And so theoretically, there is an uplift in productivity. And in terms of economics, you have diversification of income. And so now you have two products. You'll be able to sell both electricity, electrons, and crops. And so again, in theory, you should be, you're having two forms of two income pathways, which represent some kind of insurance. Unfortunately, of course, there are critics of this technology. The benefits have yet to be quantified here in the Midwest for raw crops like corn and soybean. Most of the case studies that we have seen are the small case studies focusing on specific crops like tomatoes, lettuce. Those are short crops in a small area in a specific location. And so it's kind of hard to draw some generalizable conclusions about the costs and benefits and profitability of agrivoltaics on a large scale. And the Scapes project is attempting to provide some data to answer those questions. If you haven't worked on this area before, I put some slides here just to bring you to speed. And so the underlying problem here is that PV potential, solar energy potential, is actually greatest over cropland. As you can see on this chart that was published in Scientific Reports, this figure on the x-axis is watts per square meter, and on the y-axis is the land use characteristics, type of land use. And if you eyeball it, you'll start seeing that energy output is actually higher on croplands. And the reason for that is that solar panels share the same requirements for productivity, just like crops. They both like a lot of sunshine, they like flat land, and it happens that ag land is already flat, and it already has connections to the grid, electrical connections to the grid. So it makes it suitable for installing solar panels. That explains one of the reasons why solar developers would be interested in installing their systems on agricultural land, because it's already connected to the grid. It's got road infrastructure. So that's one of the reasons for the increased competition. At the same time, here in the US, at least, a lot of, for corn and soybean, your profitability is tight, is challenging. Corn and soybean farmers make about, I would say, about $150 to $200 per acre. And so solar panels, if you look at the rent lease payments from renting land for solar leases, it's over $1,000 per acre per year over a 25-year period. So a lot of farmers would welcome that kind of investment. The issue is to find a way that allows them to continue with farming. Here's another slide that demonstrates this land use conflict between solar energy and production. And you can see that over time, I think this was also published in Nature. You can see here that over time, a lot of the PV capacity is being installed on cropland. That's the brown area. And that's increasing over the last few years, from 2016 to this data goes up to 2018. And you can see a general increase in the PV capacity that's being installed on agricultural land. Here in the US, the Department of Energy is predicting that solar, utility scale solar, could increase up to 2 million acres of land in the US by 2030. And then the question is the land use implications of that. Where's that land going to come from? Some of this would be installed on agricultural land. And so some of the land, ag land, would be converted to solar. And so this is an opportunity for farmers. This presents an investment. At the same time, it can be a problem for prime agricultural soils. So here I just wanted to show some of the the headline benefits from agrivoltaics. It looks like EV is the solution, or it provides, in theory, the solution to this land use, to reduce the land use competition. So from a photovoltaic system, a PV system, you get energy production, and from an ag system, you get food production. When you bring in EV, you get both energy production and food production, and other benefits. Like here we have water conservation benefits, especially in the dryland areas. In some cases, you also have where you have pollinators that are attached to nearby the PV system. You have biodiversity benefits, you have carbon reduction benefits, and so ecosystem benefits. So there's a lot of benefits here. And the thing is here that those benefits are hard to quantify. And there are actually a few studies that have gone after some of those benefits. And we're hoping to tackle those benefits and those issues in this study we're doing. Agrivoltaics means different things to different people. So I want to put out a slide here just showing the different forms of agrivoltaics. It can be anything in this chart on the left. If you look at the first column, that's crop production. So crops being planted in between rows of panel. This is what I'm going to speak mostly about today. The majority of my presentation is focusing on the first column. And below that, panels are raised above the ground, and some panels are vertical. They're vertically mounted to allow machinery to get through. And then in the second row is livestock. And so here are examples of agrivoltaic systems that pair PV arrays with livestock. I've been told that it's easy with sheep. That's a good combination. And more difficult with cows, which have bigger weight because they can knock on the panels. And so there's also some challenges there. And on the last column is PV systems that have pollinators to provide ecosystem services. So that's also increasingly popular. All in all, we have seen a massive increase in deployment of agrivoltaics globally. You can see on the chart to the right, between 2012 to 2020-21, there's a sharp increase in terms of installed megawatts capacity globally. There's a lot of interest in this thing. There are also critics. And as I go along my presentation, I will point out some issues that keep coming up. And so the objective of the work we are doing, in addition to all I've said so far, is we're writing this paper and we're interested to analyze land use implications, the land use requirements of meeting US solar energy targets of 1 terawatts. There is a target of 1,600 gigawatts by 2050. And the question we're looking here is what is the land use implications of that, and how might this be achieved, and which regions would this be produced? For croplands and marginal land conversion to solar farms, we're interested in the trade-off between solar income, solar profits, and crop farm income, and the external competition between crop production and solar energy. Most importantly, the question we're asking now is, under what conditions will AV be most profitable? Rather than asking the question, is AV profitable or not, the right question to be asking is, what are the conditions for agrivoltaics to make sense, for it to work for solar developers and for farmers, given the constraints of the panel, the physical size of the panels, the height, implications of the height and spacing for full sun and partial shading areas, and across different regions. It may be the case that it doesn't work across all the regions, and it might work better in some places. And so we're interested in some of that spatial variability in those benefits and costs. And finally, we'd like to understand the incentives for solar energy developers to adopt agrivoltaics. These guys are the ones bringing the investments in solar energy. And so it's important that we understand the incentives and to do this, so to ensure large-scale adoption, it has to be profitable. And so we have to look at this from the viewpoint of solar developers as well. And we're currently doing surveys with the solar industry in the US to understand their perspectives. And so to do this work cleanly and nicely, what we're putting together is a special explicit economic analysis. But to get to that, there's some steps that we've already done. And so we're looking at this spatially varying solar resource, shown this in the map. You can see here, this is a map of solar resource across the entire contiguous US. So this is kilowatt hours per square meter of sunlight. This is the amount of solar radiation falling on the ground. And you'd be tempted to, when you look at the map, you can see there's a lot of sunshine in the West. There's scaling issues here. And so it's in the Midwest. I'm speaking from Illinois. See if I can get a pointer here. So I'm speaking from here, somewhere near Chicago. Just 1 second for this to get this to work. Here we go. So I'm probably speaking somewhere here. And you won't see much variability in the solar resource. And it's partially to do with the scale of the map. If I plot this map just for one state or for one county, you see a lot more variability. And so we're going deep to look at that spatial variability in solar resource at a 4 by 4 kilometer resolution. And then we're also looking at the spatial varying availability of land. So as I go forward, I'll show you some slides with marginal land and the availability of that land where that solar could be installed. We're also taking care of agronomic aspects of AV configurations. That's crop choice. What sort of crops would work best? And we have people doing experiments on soybean, corn. We haven't started corn, but sorghum, soybeans, and other sort of high-value crops in Arizona, like tomatoes and lettuce and others. We're also looking at crop modeling of the effects of shedding on crop yields at large scale. And so when you have rows of crops in between solar panels, at some point you have panels shading the crops. And then it depends on the shade tolerance of the crops. Some crops do well, especially vegetable crops would do well with shading. And there are examples of enhanced yields due to that due to that protection from too much sunlight. Other crops do struggle with shading. There are shade intolerant crops like corn, where there have been examples and studies showing a reduction in corn yield. There's a study in Japan that reported 5% reduction in corn yield because of the shading from the solar panels. We're also looking at, we have a team of solar engineers working on optimizing the placement of the solar panels, the configuration of the solar panels, the type of panels, monofacial versus bifacial panels, orientation of the solar panels, and the dimensions of the solar panels, angle of tilt, and sort of all the PV, they're helping us to fine tune the PV parameters. And then we are coming at the end to do this economic analysis, calculating a very important metric I have here as the levelized cost of PV. This is the average cost, the per unit cost of producing a megawatt hour of electricity over the lifetime of the PV system. So this is what we're hoping to achieve. And I think that there's lots of opportunities for ag engineers, given that we understand both technology and also the crops and the interaction between the two. And so I'm going to spend a bit of time here to make sure that this is fully understood. This is probably one of the most important slides I have here. And so the design of agrivoltaics at the field scale affects profitability. And so if we look at a standard PV system that I showed in early, one of the first slides, the distance between the panels is constrained. The standard spacing is 18 feet. But for an AV system, you need at least, as you can see in this figure, you need at least 30 feet to allow equipment like a tractor to go through the panels, to go through the rows in between the panels. And so the spacing needs to be adjusted, okay? And that has impacts for cropping area. And so area for cropping, there will be area for cropping in full sun, and there will be some areas, because of the panels, there's going to be some areas in partial sun. And so immediately there's a loss of land, loss of the 6 feet. So the 6 feet that's the panel width. That is the area directly underneath the panels. As you can see here, there's an area underneath the panels. You're not going to be able to farm there. Although we will relax this assumption later, and we show an example of a scenario with smart equipment that can go underneath the panels. There is some loss of land for buffer area at the field ends to allow a planter or a tractor to turn, to allow for a turning radius that's sufficient for equipment. And so this is the sort of design, this is the configuration, this is the question. What is the optimal configuration? What should be the optimal spacing? What's the height? The height is also important. They say that gravity is the enemy of agrivoltaics. In other words, as you go higher, you have these wind loads. And so you need to provide reinforcement for the panels. And so your costs will start to go up. Capital cost for AV is high. The current estimates I have here is $2.66 per watt DC that are current, compared to that's just 1.15 for PV, which is ground mounted. And so the point here is, as you go, the higher you go, the costs start to escalate. And so that's the challenge. And so what we're trying to do is to tease out the configuration. What is the best configuration that would allow farm equipment to go through, that would allow mechanical harvesting of the crop, but which still makes sense because now you're losing land. And so you're losing energy generation. So this is going to affect project economics. And today I will share examples of the impact of this on profitability. If you do have any questions, you can put it in chat, and I can return to these questions at the end. And I put this slide just to show you what I mean by capital costs. And so on the left here, the first bar here is this is your PV. This is a ground-mounted PV. That's a typical PV system that is ground-mounted. And the capital costs, install cost here is in dollars per watt, is 1.53 or something like that, $1.53 per watt. And then when you start adding things, so PV plus, so look at pollinators, PV plus I moved to, so this is PV plus livestock. When you bring in livestock, you need to reinforce the PV stands. So your costs start to grow up. And finally, when you come here, the last one is PV plus crops. The very last column here. $2, 2.53, and these have gone up. And so this is a regular reinforced mounting for the PV panels, and you can see there is a sharp increase in the capital costs. And these are the drivers of those costs. These are the components. The biggest one being this yellow part, the module. I believe this is the module cost. And there's different elements here. You can see, I hope you can see that. There's electrical balance of system costs, structural costs. Also, they look like a big part of it. And there's all kinds of things, permitting fees. So these are the different components of the costs. This will go up as you start increasing the height of the PV system. This is very, very important because this is going to have a huge impact on profitability. And if we look at it from the point of view of solar developers, this is where we need to have some discussion. And so we don't know what an AV farm is going to look like in the future. And to analyze profitability of those farms, we've developed scenarios. We have 12 scenarios, what the farm might look like here in the US. And so I'm just going to briefly outline what the scenarios mean. And so on the first part of the slide here, on the left side, you have rows of props interspersed between solar panels. This is what we know as an AV system. Okay, and so some land is going to be lost in between the panels, and that's going to be used for farming. There will be enough space for machinery to go through, and so that's going to affect generation, and that might also increase costs. So those are the two things we're weighing, and that's what you have on the first side here. You have scenarios 1, 2, 3, 7, 8, 9, 10, 11, 12. And what we're going to do with these scenarios is we're going to play around with the spacing in between the panels. In some cases, it's going to be more than 42 feet. In some cases, it will be less, it will be 30 feet, 36. And then we're going to go up and go down and look for, we're sort of looking for the sweet spot here in terms of profitability. And then scenarios 4, 5, 6 is depicting a situation where you have almost two separate fields. And you have, sorry, trying to get to the right. Yeah, here we go. So you have the PV panels on one side of the field. And this could be 50-50 split, it could be 75-25% split. So we have all the PV panels on one side, and you have props on the other side. And that is probably easier for solar developers. And so this portion is the sort of PV part, and that's the crop part. And so that is also agrivoltaics, because it's not integrated, it's not fully integrated like in the first few scenarios, but that is also representing a form of a potential scenario where solar developers or farmers might decide to allocate a portion of their field, 50%, 60 or 70% to solar panels, and the other corner or the other half, the other piece, or whatever is left of it, crops. And then we're going to calculate how much this is going to cost. And then we're going to calculate returns. We have prices, we have crop yields, we're going to estimate energy yield, and then we're going to calculate the profitability. And for all of these scenarios, I'm going to mostly stay around with the reference scenario. We have something called the reference scenario. All these other scenarios are a variation of the reference scenario. If I go back one slide, another slide, this is the reference scenario. Our reference scenario has got these dimensions. It's got spacing. It allows this farming area up to about 42 feet, pole to pole between the panels. It's got a height of 8 feet to allow for, so those are raised panels. Of course, that has implications for capital costs. And then the rest of the scenarios are going to be variations. And so in some, I can pick another scenario. For example, we can take scenario 10, the reference with no farm buffer. So we want to use that area for either PV or for crop production. And then we're going to compare this with utility scale. The control is going to be utility scale and all crop. So I'm going to be presenting results of profitability for these 12 scenarios and compare them with the control. When a solar developer or landowner chooses to do all PV or chooses to do all crop, that's where this is heading. First slide I want to share is that there's really a trade-off between PV and crop output at the field scale. So all of this is happening, I should say, in the reference scenario, we're assuming a farm size of 80 acres. This is basically the average farm size in Illinois. We just picked that arbitrarily. to start somewhere. We say, assume the farm is 80 acres. And so we're going to subdivide the 80 acres into a PV part and into the crop part. And so here is a plot for the 80 acres. This is a plot showing PV output and crop output on the y-axis. So these are the 12 scenarios. And immediately you can see that there is a trade-off. There is a downward sloping trend. When you increase PV production, you are giving up a little bit of crop production. And vice versa. If you increase crop production, you have to give up a little bit of megawatt hours of electricity. That's why we have this downward slope. Oh, I got it. And so two extremes I would like to point out is here. So if we allocate the entire 80 acres to produce electricity, you will have zero crop production, as you can see on the y-axis, and you produce maximum electricity output of about 27,000 megawatt hours per year. But then you don't have any crop output. The other point is here. We're going to allocate the entire land. It's going to stay as a farm, producing only soybeans. And that's what you get. And so you could think of a production frontier here. And it doesn't have to be the straight line. I just used this straight line to demonstrate this trade-off. It would actually be a curve going like that, going over this point, coming down here, all the way down here. Okay, that's our production frontier. And so what we're trying to get here is we're looking for the sweet spot that would maximize both energy output and crop output. But there's going to be a trade-off in this kind of calculation. So basically, this is the thing. Some scenarios will be more profitable than others. Okay, some of it will not work. And solar developers might prefer a bigger share of land going under PV than crop because of electricity prices are much higher. So we're doing this calculation to look at those different scenarios and different combinations, and I'll share some of those results in the next slides. Now I want to speak about here the land equivalent ratio and profitability. This is very important. In the literature, in most of the literature, especially on the physical science, there is a lot of optimism about the land equivalent ratio because you're using the land to produce two outputs, electricity and crop yields. And in theory, you are doubling you're trying to double your land use or your outputs. And so you have an increase in productivity. You have a perceived increase in productivity. And so this land equivalent ratio, the way it's calculated, if you don't work in this area, I'm assuming some of you work in this area, it's the ratio of yield, crop yield in an AV system that's divided by crop yield in monocrop, plus the ratio of electricity yield in PV system divided by electricity yield in a pure PV system. And so you have this, and my handwriting is terrible here, but I'll try and write this down. So you have that. So you have this, Y is crop yield in AV. This is important. Divided by crop yield in pure cropping system. Let's just call it C. And then we're going to add that to electricity yield, YE, make it different, in AV, divided by yield, electricity yield in PV. Sorry about that. Okay. And for some reason, these always, for AV systems, this is a physical metric. So this LER is going to come out greater than 1. As you can see here on my x-axis, LER goes up to 1.25 and beyond. And for a lot of papers that have been published, especially in the physical domain. This is good. And this is used to justify saying, AV leads to increased productivity. The problem is that LER is actually not sufficient. It's necessary, but it's not a sufficient condition for AV adoption. Because as I show in this slide, you can achieve an LER greater than 1 with negative profits. This is what we have here. This is what this slide is showing. So you can see here on the x-axis is the LER, land equivalent ratio, and on the y-axis is profit. And all of these points, negative profits here. And so, and a few scenarios. So separate crops. Those are 6 scenarios I mentioned, 4, 5, and 6, where you had separation between the panels and the crops. Have positive profits. So this is a 0 profit line. And these guys, this makes sense. So this is about $5,000. They're making about $5,000 per acre. And so it would make sense for someone to actually continue farming crops, just producing crops, rather than doing these scenarios, given these parameters I have below, which I will explain in a minute. And so this starts to show that the emphasis on LER could be misleading. What we need to look at is profitability. Yeah. Because other things drive profitability more than LER. For example, capital costs. So the capital cost of $2.6 per watt is driving down profit, and labor, also the operational costs. And importantly, policy support, which I capture here using the renewable energy credit. Here is $6.6 per megawatt hour. That's extremely important. If we take away this credit, a lot of these points would be negative. And immediately, the thing that becomes obvious is that solar developers are not going to want to do this if they're not going to want to do any of these scenarios, which lead to negative profitability. So then what happens in the next scenario? Let's look at the next scenario. Back to land equivalent ratio and profitability. Again, I have identical plot. What I've now changed here is I've increased policy support. I'm assuming a higher REC, renewable energy credit. I've doubled it from $6 to about $13 per megawatt hour. And also capital costs, we'd assume that they were very high, but what if capital costs were not that high? What if through the market or through some mechanism, capital cost increase are moderate? Let's assume 30%. And so we have this. Now, what you have is a lot of scenarios, a lot of these AV scenarios are now profitable. And they can compete with PV. So PV is somewhere here. It's always, this is just 100% PV. It's always going to be more profitable than most of these scenarios. But we start to see some movement towards profitability. A lot of these scenarios are now becoming profitable. And here again, you can see the dynamic has changed, and you start to see an increase as you increase LER, we're also increasing profitability, conditional on lower capex and conditional on more policy support. And so the takeaway message here is that AV is feasible with lower capital costs. Lower capital costs and a little bit of policy support would help. So this is really important because if you look at these two slides, solar developers would not want to do this. But this looks more feasible, okay? And so this is the calculations I wanted to share. I won't go into too much details about this. These are static, comparative statics, but we are trying to do more robust calculations of this profitability. And now what we want to do in the next steps, some of the work we're doing is scaling out. So we have this 80-acre farm in Illinois. Assume that there are so many of those around the US. So we want to extrapolate from a single farm in Illinois across the entire US. And that's, I'm going to just show you a hint of that, how we're going to do that. And so we're looking at the costs, levelized cost of energy. If we do that, if we have so many of those 80-acre farms, we have them spread all over the US, how much will it cost? What's going to be the cost, the average cost of producing a megawatt hour across the different scenarios? So as I mentioned, here is the scale. This shows the costs. If we focus for a minute on the map showing the PV only, so PV is always going to be cheaper because of the density of solar panels, because the panels are closer together. There's no crops in between. And so it's producing the maximum amount of electricity generation. And so the PV map, let's see if I can pull this up here. Basically, scenario number 13 here is got the least cost. And you can see that this is spatially varied. Obviously, areas to the west will have the least cost compared to all of the other areas. For agrivoltaics, though, these scenarios are costly because we are losing land in between solar panels, planting crops, and you probably need very high crop prices to lower those costs and to increase profitability. So a lot of the maps for the AV scenarios are going to be, they're going to look expensive. So if I look at this, so these are my 80-acre farms all over the expanded, extrapolate across the entire US. And that's the cost of producing a megawatt hour, plus the different grids. All these are the grid points. So this is going to be more expensive compared to just doing pure PV, which I want to highlight. If I can pull, I got it. These two. Here we go. So that's PV, pure PV. This is our reference scenario. So this is going to be more costly to do that. We wanted to be transparent about the cost of doing this. It's going to be more expensive to do it, but there is also unquantified benefits. And as we go along, we will try and capture some of those benefits. And we're fine-tuning these scenarios to make sure that the area that's going under crop, the areas going under PV, it's all correctly calculated. And we're presenting very, very accurate figures. So this is the levelized cost of doing. This is the cost of doing solar at large scale across the different scenarios. PV is always going to be the cheapest, and AV scenarios are always going to be more expensive. And you can look at the range of costs from $40 per megawatt hour all the way to $1,500. Some of this is going to be prohibitive, going to be too high to do. And that leads me to another slide. So I won't spend too much time on this. All I want to say, this is supply curve, because we want to identify the cost of meeting the solar energy targets. Remember, I mentioned the 1,600 gigawatts of energy by 2050, and the cost of doing that and which areas would contribute to doing that. So we have a supply curve for that. And so on the x-axis is capacity generation, gigawatt hours, cumulative. So the lower cost grids are entering fast, they're coming fast. And then on the y-axis is the LCOE, the number I've been talking about for a bit, the cost of producing a unit. And as you can see here, PV, all the PV is to the right, and all the supply curves for the scenarios are to the left. And so it's always going to be more expensive to do AV scenarios compared to PV. And they get very expensive after, if you draw a straight line here, for example, you can see this, it just gets very, very expensive after here, it just goes high. And so AV scenarios cost more for generation and transmission and have lower cumulative capacity. And transmission costs are also a constraint here. It's going to cost money to transport energy. So you can imagine the interconnection costs, cable costs, cost of power lines, spar lines, from the farm to the electrical substations. So that's what is driving this. So when you add the transmission costs, you can see there's a huge jump it pushes the curves, they all push to the right. So there's an increase in cost due to transmission. And so if we have a target, let's say we choose one, we draw a straight line. Trying to get to my, here we go. So let's draw a straight line here, right here, straight line going up. So if that was the target, PV can meet, pure PV would meet the target at a lower cost of just over $50 per megawatt hour. And this scenario, with the blue scenario, which is the low farm density, would be a bit more expensive. Here we go. At over $100. That's going to be over $100. And so this is where we're going with this work. We want to demonstrate the cost of meeting the targets and where it might be cheaper to meet those targets, which parts of the country. I won't be able to go into that now because that's the work we're doing currently. Those are the calculations we're working on at the moment. But we would like to identify which parts of which grids would be able to provide those targets and at what cost, at a lower cost. And so with this in mind, with some of these results in mind, we have started approaching the solar industry. We've started having discussions with the US solar industry. We're currently talking to several solar energy developers. We're having focus group discussions. We've had three focus group discussions with them to understand their perspectives. While I am excited about PV, about agrivoltaics, I fully understand there are some critics and there are some concerns that have to be addressed, and we've tried to do that we're trying to do that in this work that we're doing. And so these are the key issues that have been mentioned in those discussions. I want to just provide a few bullet points summarizing solar developer perspectives on that. It's heterogeneous response. There is interest, but they would like to do it in a way that is profitable and meaningful to them. And so one of the concerns here they have is the technology still needs to be developed. So the need for off-the-shelf AV technology that works, and also lower costs, especially the capital costs. Those are really important drivers for them. They wanted some clarity on government regulations and community requirements. And the big one is liabilities. They're concerned about liabilities and insurance when farmers, when you allow farmers to plant crops near solar panels. The question then is, who will provide that insurance? And we also had to wrestle with this issue when we were installing our own, when we were growing crops in between solar panels at our project sites. There was concerns about equipment, a tractor or a planter damaging the solar panels, and who is going to provide that insurance? And you're talking about $1 million in insurance, so that's a big figure. So that's quite a challenge. There's community opposition, not always for legitimate reasons, often for a lot of other myth beliefs and not in my backyard attitudes. We've encountered a little bit of that. A lot of solar developers do not want to do the farming. They want to focus on producing electrons. And here is a quote that I took from one of them. We would like to focus on making electrons and let farmers do the crop cultivation. There are also some concerns that this may not lower land costs for solar. Instead, it actually adds to the requirement for more land, because now you need buffer areas, you need more land for a turning radius of the tractor, and all of that. And so this kind of concerns. And so there is definitely interest among solar developers but they would like to do this in a way that is profitable, in a way that makes sense. And it's early days in the industry, very, very early days in the industry. There are heavy farms here in the US. Most of them are still small scale, but there's a lot of discussions on how best to do this. And we also had focus group discussion with farmers, and farmers were very excited. There's a lot of interest. There's overall interest in the idea of agrivoltaics. Most of them were not aware of this agrivoltaics. The first time they had the word, it was a new concept, but they welcomed the lease payments, especially the farmers that were approaching retirement. Some of those were interested in considering it. So there is interest in incorporating agrivoltaics with livestock and sort of the non-productive acres of land, sort of the marginal land, which I will show in one more slide. Some farmers were interested in taking risks, and so they were thinking of a revenue sharing agreement where they don't just lease the land, but they actually get into some kind of revenue sharing contract with solar developers. And agrivoltaics can enable some conversion to solar while preserving the way of life of farmers. And so a lot of farmers express this sentiment that we are producers. We like to produce something, and it's hard to see our land just go to solar panels. And so AV would definitely help ease these concerns. There were also some additional concerns that were raised in these focus group meetings. For example, what happens after 25 years? So these solar leases are typically 25 years. What's going to happen at the end? Impact on the land? Is it still going to be in a form that can be farmed? What's going on with all the concrete? And so those are questions that some farmers were asking. There's issues of compatibility with current equipment. So the size of the current row crop equipment, like combine harvesters, tractors, is not compatible with the panel dense solar farm. Imagine a big combine going through would require a lot more space in between the panels. So those are the kind of issues. Community opposition is there, purchasing land in their community. And farmers do not have this capacity to set up a utility scale on their own. The financing requirement, the capital cost is about $1 million per megawatt capacity. And so solar developers and farmers are in a way interested, although with some concerns about how this could be done. And so in the next steps, and we use a lot of time. So in the next steps, we are looking at doing this on marginal land. So this map basically shows areas which have marginal land. As you can see in the Great Plains area, there is a lot of marginal land here. And so it may be possible to, how far could marginal land take us? How much of the solar targets could be achieved just by using marginal land? We also need to incorporate the shading impacts. And I think that could be opportunities for ag engineers to study the interaction of panels and crops and be able to incorporate some of these impacts on crop yields and also potential impacts on electricity output. We're expanding across the entire US, and we're doing sensitivity analysis and solar survey. So this is, I believe, the last slide I have. And that's the project website. That's my email. The project director is Professor Madukana. I'm project manager, and I would love to answer any questions that you have. Thank you so much.
Okay, thank you, Paul. Yes, we've got a few questions. The first one is from Robert Smits. If you want to unmute and ask.
Hello, can you hear me?
Yes, I can hear you.
Oh, hi. Yeah, sorry, we'll switch on my camera. No, I had a question because, thank you very much for the presentation, very interesting. And the question is, in fact, if there's any experience with, let's say, dust and pollen on agricultural, if you're in an agricultural setting with the photovoltaics. Because it's different, let's say, than an environment where you have a lot of asphalted roads and where you put them on the top of, let's say, industrial buildings.
Yeah, so the issue of dust, there's going to be some dust accumulation on the panels, and there could be a cost there to remove the dust. But there's also a benefit from having farmers operating underneath the panels. One of the benefits is vegetation management. When you have all of this vegetation underneath the panels, that's usually a cost to solar developers to maintain that vegetation. But when you have farmers, they will take care of that cost. That cost goes away. So that's an advantage. The dust removal is interesting. I'm not sure what the cost is, but there's a small cost of having.
No, I'm just asking because we had a project and there were some, let's say, non-asphalt dirt roads, and we were not sure, let's say, if that was a good idea or not, and we couldn't find any, let's say, literature being published on this. So.
Yes, there is one paper that looks at dust accumulation on panels, and I could share that.
That would be great.
I could send an email to that. There's definitely a cost to that, but there is benefits from having farming activity.
No, that's true. Didn't consider that. Yeah, thank you very much.
Sure. All right, super.
Okay, I think Brian, Matthew, I think your question's probably been answered, but you did have another question about wind power, if you wanted to ask that.
Thank you, Charlie. And Paul, thank you very much indeed. A very interesting presentation. You did answer the question on insurance. I was sort of imagining how careful you'd have to be driving your tractor with whatever you're pulling behind it through between the panels. Also, of course, you've got the issue of wind. I was going to ask about if anyone was looking at wind power, but before that, there is also the issue of the tornado belt, and which is another insurance worry, I should think, for the states. But I guess that would be a cost which you'd have to forego in any case.
Absolutely.
But what about wind power and agriculture? Because that must be a common thing already in much of the hinterland of the United States.
Yes. So we are not specifically looking at wind, but there's a lot of wind technologies here that is being set up around these areas. What we will do is we will compare LCOE, the average cost of deploying solar versus the cost of doing wind. At this point, we're mostly focusing on solar panels because of the potential compatibility with ag farmers and opportunities. But yes, wind is also growing. In fact, we are in the wind belt. There's a lot, as you say, there's a lot of wind here. And there's a lot of investments going into wind. But in this project, we're not focusing so much on wind. There's a lot of solar developers that are moving around, are interested in deploying solar panels on ag land, and that's what we're mostly focusing on. But yeah, that's another. I guess it's about the energy mix. Then you have both solar and wind and all of that. It will improve the sort of energy mix, portfolio of energy.
If I could just ask a corollary to that, and that is, have you thought at all about the use of the energy perhaps for agricultural equipment? So, electric tractors, for example.
Yes. So some of the energy produced, not all of it will be put on the grid. Some of it will be consumed on the farm. Residual use would help offset. In fact, that's another cost saving that would reduce on-farm costs. Energy use. So some of that energy will be used immediately on the farm. And in fact, that's identified as a potential benefit.
Thank you very much.
Yeah. Of course, the excess will be, a lot of that will be going onto the grid.
Sure.
Yeah.
Okay, we've probably just got time for one more question. I'll miss my question now. I think is it George G. Sly? I presume it's George, is it?
Oh, yeah, it is Charlie, sorry.
Hi, George.
Hi. Yeah, no, it's just whether the cropping systems that you've looked at between the panels are always or all your research has been on annual crops rather than perennials, shrubs, trees, etc. I know you'd think, why would you want to put trees between them? But if you specifically think of shallower crops that, say, berries, fruit, and nuts that aren't tall and aren't going to shade, I would just think that might be a lot less risk and a lot less passes through the field with dangerous equipment, etc., etc.
You are completely right. And so we have 3 project sites. So in Illinois, the dominant crop here is corn and soybean. And this is a rain-fed region. So in Illinois, we're focusing on soybean. But in Arizona, they're looking at tomatoes and lettuce and sort of shorter crops, and also higher value crops, things that might make more sense. And so it might be the case that it works much better in Arizona. But we in Illinois, we cannot take the electricity from Arizona, because you can imagine the transmission costs bringing that electricity. And so we also have to consider where the demand for that energy is. Although, it looks like it may work better in Arizona, the transmission costs of moving the energy from far off locations with a lot of sunshine where the population is might also be high. But the point you're making is right. It might work better with high value crops, short crops, things like lettuce, tomatoes that enjoy that shading, that have higher yields. And that may be the case. And so we think that AV is going to depend on the location. The design, the optimal design is going to be location dependent. It's going to, depending on the climate. Let me stop by saying that there's 5 C's for agrivoltaics. You got to think about the climate, you got to think about the crops, you got to think about compatibility and cost. And one more is just collaboration, collaboration between solar developers and other entities involved to make it work.
Okay, thank you.
Absolutely.
Okay,
thanks for listening.
We're just slightly over the hour, so I'll draw things to a close. So thank you, Paul, for an excellent presentation and taking the time out and getting up early to do that for us. It's very appreciated. I'm sure everybody found it extremely interesting and thought-provoking. I'd like to thank everybody for joining us today and hope you will join us for our next lecture on the 12th of September, where we'll be joined by Jonathan Lodge from City Farm Systems. Also, while I'm on, I'd like to remind people that booking is now open for our annual conference on the 1st of November. And the conference this year is going to be looking at the efficiency and sustainability of food production. And for reasons of inclusivity and removal of geographic boundaries, we've chosen to go online this year. The event's now on our website, so please get yourself registered. So all that's left to say is thanks again, and we'll see you next time. Thank you. Bye-bye.